Good morning, everybody. This video is going to cover 12.4, 12.5, and 12.6, where we look at mass to mass stoichiometry, volume to volume stoichiometry, and mass to volume stoichiometry. Let's get started. Okay, so remember, we were talking about moles last set, and moles are important, but in a lab, we will usually measure substances out by mass, which is usually going to be in grams because we can't measure moles. We don't have a scale for moles, and we can't count atoms or molecules. So we need to know how many grams we're going to be measuring for a certain reaction. So most of the time, you'll know how much mass of one thing that you have or you want, and you need to figure out the mass of another thing you want or you need. So for these problems, we'll need to calculate molar mass and use the mole ratio from a balanced equation. All of this should hopefully be reviewed from 12.1 through 12.3. So let's do an example problem. Here we have NH4NO3 solid is going to yield N2O gas and 2H2O liquid. In a certain experiment, James decomposes 45.7 grams of ammonium nitrate, which is this guy here. Find the mass of each of the products formed. So we want to know how much of our nitric oxide we make and how much of our water we make. Okay, so here's our example problem. Steps are the same as last time. Step 1, you write out what you know and write what you're trying to figure out. Step 2, you solve for the problem. And step 3, you check if your answer makes sense. So what we know is that James is decomposing 45.7 grams of ammonium nitrate. What we want to know is the mass of each of the products formed. So we want to know our N2O, and we also want to know our H2O. Okay, so there's what we know and what we don't know. We know that we have 45.7 grams of the ammonium nitrate. We also know our mole ratios and our molar masses, and what we don't know is the mass of both of the products. Okay, so how do we set this up? What we're going to do is we're going to go from what we know, which is our grams of ammonium nitrate, over to our moles of ammonium nitrate, and then to our moles of each of our products, here and here, and then our grams of each of our products, here and here. So this guy is going to be kind of like a little map for us, so we can figure out how to go from what we have to what we want to have. So that's a little map. Okay, so let's go ahead and try to solve this. Okay, so there's my map in this upper right corner here. And let's also need our periodic table. So we have our hydrogens, nitrogens, and oxygens here because that's what we have in our formula. And so we start with what we know. You can't start with what you don't know, so you have to start with what you know. We know we have 45.7 grams of the ammonium nitrate, so we start there. And if you have grams, we're going to start to set up our different fractions. We can see from our map up here, we'll need 1, 2, 3, 4 different parts of our equation. So 1, 2, 3, 4 different parts of our equation. We're starting with 45.7 grams. And we want to get rid of the grams of the ammonium nitrate. So if we have them in the numerator right here, we're going to need them in the denominator down here. So the same idea is if you're in math class, you might have like 100 divided by 100. That cancels out. It's just 1. 3 divided by 3 cancels out. That's just 1. 495.27 divided by 495.27 cancels out. That's still just 1. So the grams of ammonium nitrate will cancel out by the grams of ammonium nitrate that are being divided down here. So where did I get this number from? 80.06. 80.06 is the molar mass of my ammonium nitrate. And how do I figure out my molar mass? Well, we have 2 nitrogens, and each nitrogen weighs 14.07. And then we also have 4 hydrogens, and each hydrogen weighs 1.0078. And then we have 3 oxygens, and each oxygen weighs about 15.999. So when you figure out the molar mass by multiplying our molar masses by our subscripts, then you can figure out your molar mass. So 2 nitrogens plus 4 hydrogens plus 3 oxygens which we use our molar masses from up here, are going to give us 80.06. And if you want to pause the video and just double check my math on that, you can. Okay, so that's our molar mass. So what does that mean? It means that 1 mole of ammonium nitrate weighs 80.06 grams. So we have my moles on top. This fraction here, or this conversion factor, is called a molar mass. Next, we have 1 mole on top and we have 1 mole on the bottom. And how do we know that the 1 mole goes on the bottom? We want to be able to cross out the unit moles of ammonium nitrate and the units moles of ammonium nitrate. Remember, what we want in the end is we're trying to find the mass of each of the products. And so we want to get rid of the ammonium nitrate. Okay, so this is now where we're going to use our mole ratio. Our mole ratio, we're going to look at our equation up here, our balance equation, to find our mole ratio. We know that we have 1 mole of the sodium nitrate, which is right here. The coefficient is 1, and that's where I get this from, 1 mole of the ammonium nitrate. And then I'm trying to move to figure out one of the products. So here's one of my products here, my nitric oxide. And so the coefficient is also 1. So my fraction, or my conversion factor up top, is going to be 1 mole of nitric oxide. And then we want to get rid of the moles of nitric oxide because I'm trying to figure out the grams of nitric oxide. So if I have 1 mole of nitric oxide up top, I'm going to need 1 mole of nitric oxide on the bottom, and that'll cross out my moles of nitric oxide. And then 1 mole of nitric oxide in grams is 44.02 grams. And how do I know that? If you look at nitric oxide, it has 2 N's, so each N is going to be 14 grams, and it has 1 O, and each O is going to be about 16 grams, and you add them all together, you get 44.02 grams. So one way that you can check that you have set your problem up correctly is you make sure that all of your units cross out and you end with the correct units that you're trying to get to. So grams of ammonium nitrate cross out, grams of ammonium nitrate cross out. Moles of ammonium nitrate cross out, moles of ammonium nitrate cross out. Moles of nitric oxide cross out, moles of nitric oxide cross out. What we're left with is just grams of nitric oxide, and I'm trying to find out the mass, which is grams, of nitric oxide, which is one of the products. So that looks good. My setup looks functional. And the answer is 25.1 grams of nitric oxide. Okay, so the question was asking about the mass of each of the products. So I've only figured out one product so far. I have to figure out the other product as well. So a good thing for you to do right now would be to pause this video and see if you can set up the way that we're supposed to figure out the grams of water that we would get from 45.7 grams of ammonium nitrate. All right. Hopefully you paused, hopefully you figured it out, and I'm going to show my setup for that. We start with what we know, 45.7 grams of ammonium nitrate. We know that we're going to need 3 conversion factors according to our little map up in the corner. And if we have grams of ammonium nitrate up top, we need grams of ammonium nitrate on the bottom. And this is my molar mass of my ammonium nitrate. And then we have 1 mole of ammonium nitrate up top. We need 1 mole of ammonium nitrate at the bottom. And this is where we're going to bring in my mole ratio. And my mole ratio is 1 mole of ammonium nitrate. And it's actually going to be to 2 moles of water. And how do I know it's 2 this time instead of 1? If we look at our equation up here, we have a coefficient of 2. And so we'll have a 2 on top. And then we have 2 moles of water up top. We need 1 mole of water on the bottom. This is going to be the molar mass of our water. And the molar mass of water is 18.02 grams. And that comes from 2 hydrogens, each of them weighing about 1.0078 grams. And then 1 oxygen weighing about 15.999 grams. So then we can double check and cross out all of our units. We've got grams of ammonium nitrate, grams of ammonium nitrate, moles of ammonium nitrate, moles of ammonium nitrate, moles of water, and what we're left with at the end is grams of water. And we can calculate and multiply 45.7 times 1, which is 45.7, times 2, which is going to be about 91 grams, times 18, which is, I don't know what that is, and then you'll get some sort of number in your numerator. Then you can divide by 80.06 times 1, which is 80.06, and our answer should be 20.6 grams of water. And then for this kind of problem, you can check that your answer makes sense. And the way you can do that is you can add together your answers. 25.1 grams plus 20.6 grams, these are your products, and they should equal your reactants, which is what you started with. This is called the law of conservation of mass. You can't add mass or lose mass through the course of a reaction. So I started with 45.7 grams of stuff, of nitrogen and hydrogen and oxygen, and I'm ending with 45.7 grams of stuff, nitrogen, oxygen, and hydrogen. Okay, let's move on. Okay, so let's talk about volume to volume stoichiometry. We know how to do mass to mass stoichiometry, hopefully. And if you don't, you want to go back to the previous part of this video. But masses are great when you're working with solids. But sometimes volume is going to be the better measurement for liquids or gases. So remember that at standard temperature and pressure, which we call STP, which is when we have 0 degrees Celsius or 32 degrees Fahrenheit and 1 atm or atmospheric pressure, 1 mole of gas, any gas, will take up 22.4 liters of space, which is our volume. This makes volume to volume problems that we do at STP pretty easy. So let's take a look at an example. We've got our N2 gas plus our O2 gas, 2O2 gas, which is going to yield 2NO2 gas. Let me back up. Let's take a look at an example. We've got our N2 gas plus our 2O2 gas plus 2NO2 gas. So nitrogen gas plus oxygen gas is going to yield nitrogen dioxide. We have 1 molecule of nitrogen gas because there's 1 in front of the nitrogen as our coefficient. There's 2 molecules of oxygen gas, and then that's going to produce 2 molecules of nitrogen dioxide gas. That's the same as saying 1 mole of nitrogen gas plus 2 moles of oxygen gas is going to yield 2 moles of nitrogen dioxide. They're not the same amount. A molecule is going to be smaller than a mole because a mole is 6.02 times 10 to the 23rd molecules, but we can kind of still use the coefficients for the same thing. Because in the lab, we're not going to be measuring out 1 molecule, 2 molecules, 2 molecules. We're going to be measuring out 1 mole, 2 moles, or 2 moles. And we can also use that to convert over to volume. 1 volume of nitrogen gas is the same as 1 mole. 2 volumes of oxygen gas is going to be the same as 2 moles. And 2 volumes of nitrogen dioxide is going to be the same thing as 2 moles. And when we have our balance equation up here, what we can do is we can figure out all of our mole ratios. So here's my balance equation and our mole ratios. So for example, how much nitrogen do we need for every oxygen? Here's my nitrogen. Here's my oxygen. We need 1 nitrogen molecule, 1 volume, 1 mole of nitrogen for every 2 molecules, 2 moles, or 2 volumes of oxygen. So that's my first mole ratio. I can also flip that, and it's basically the same thing, except oxygen's on top and nitrogen's on the bottom. Another mole ratio I can do is I can look at the relationship between nitrogen and nitrogen dioxide, and it's 1 mole of nitrogen gas to 2 moles of nitrogen dioxide, or 1 volume of nitrogen gas to 2 volumes of nitrogen dioxide. And again, we can flip that, and it's the same idea. And then our last relationship that we can have is looking at oxygen and nitrogen dioxide. So it's going to be 2 moles of oxygen to 2 moles of nitrogen dioxide, or 2 volumes of oxygen with 2 volumes of nitrogen dioxide, or we can flip that, and those are our 6 mole ratios for this particular problem. All right. Okay, so let's do an example problem. We've got C3H8 gas plus 5O2 gas is going to yield 3 CO2 gas and 4 H2O gas. And our question is, Blessing wants to combust 0.650 liters of propane. What volume of oxygen does she need to combine with it? And then what volume of carbon dioxide will she end up producing? So our same steps. Step 1, we write out what we know, what we're trying to figure out. Step 2, we solve. Step 3, we check to see if our answer makes sense to us, that the number's not too big or not too small. Okay, so what we know is that we have 0.650 liters of C3H8. That's going to be our propane. We know our mole ratios. As long as you have a balanced equation, you know your mole ratios, or you can find your mole ratios. And then you need to figure out your unknowns. What we want to know is the volume of O2, and we want to know the volume of CO2. Okay, so how do we set that up? We start with what we know. We've got 0.650 liters of propane. And if we have liters of propane up at the numerator at the beginning of our equation, we're going to need liters of propane at the bottom. Because remember, like what we said last time, we've got to cross these guys out. We've got liters of propane, and what we're trying to move to is volume of oxygen or volume of CO2. So we want liters of oxygen and liters of CO2, so we have to get rid of the liters of propane. Okay, so now we're going to use our mole ratios. We have that 1 liter of propane, and if I'm trying to figure out oxygen first, I know I have a liter of propane. How much oxygen do I need for every liter of propane? And I need 5 liters of oxygen for every liter of propane. And how do I know that? I can figure that out from my mole ratio. Up here, I've got 1 liter of propane for every 5 liters of oxygen. And so then we're able to set up our problem. 0.65 times 5 divided by 1 is going to be 3.25 liters of oxygen. Okay, so our next problem, we are also asking, well, how much volume of CO2 will I make if I have 0.65 liters of propane to start with? So again, we start with what we know, 0.65 liters of propane, and we want to get rid of the liters of propane. So it's in the numerator here, so it's going to need to be in the denominator of our conversion factor. And then we need to use our mole ratio. So how much propane do we need for every CO2? And if we look up at our balance equation, we're going to need 1 liter of propane, which is going to produce 3 liters of CO2. So that's what's going to go on the top. And then we can just check to make sure that we set up our problem correctly, and we can cross out our units and only end up with the units that we want. So we cross out the liters of propane, and then we're just left with the liters of carbon dioxide. And that's going to give us 0.65 times 3 divided by 1 is 1.95 liters of carbon dioxide. And that's our problem. You guys should note that these numbers aren't going to add up the same way as mass. When you add together 0.65 of our propane reactant with 3.25 liters of our oxygen reactant, that's not going to equal our products. Our products are going to be 1.95 liters of CO2. And if you do the math, it's going to be 2.6 liters of H2O. Those are not going to equal each other. The volume is not going to be conserved. Mass is conserved from the beginning to the end of a reaction, and atoms are conserved, but volume is not conserved. And if you want to, you can go ahead and try to set up a problem so you can figure out if we have 0.65 liters of propane, how much water would you make? And your answer should be 2.6, but you would need to figure out how to set that up using these two as an example. Okay, clear off the screen. Okay, next let's talk about mass to volume stoichiometry. So here's our problem up here, or our equation. We have 2 aluminum solid plus 3 H2SO4. This is going to be sulfuric acid. Aqueous is going to yield Al2SO4, 3 aqueous, and 3 H2 gas. This is aluminum sulfate. This is aluminum sulfate, and this one over here is hydrogen gas. Okay, so Nadi's going to go ahead and react 2 grams of solid aluminum with aqueous sulfuric acid. And how much hydrogen gas does she end up producing with that? So same steps, write out what we know, what we don't know, solve a problem, see if we think our answer makes sense, that our number is not too big or too small. So what we know is that we have 2 grams of aluminum. We can figure out the mole ratios because we have a balanced equation, or we could balance the equation if we don't have a balanced equation. And then we can figure out our molar masses as long as we have a periodic table. And what we're trying to figure out is how much hydrogen gas we're going to end up creating. So let's go ahead. And what's our setup look like for this? We want to go from our mass of given to our moles of given, to our moles of our unknown, to our volume of our unknown. So we're starting with our grams of aluminum, then we'll move to moles of aluminum, then we'll move to moles of hydrogen, and then we'll finally move to liters of hydrogen because that's going to be our volume of hydrogen. Okay, so we've got our 2 grams of aluminum, and we can set up our problem. We know that we're going to need 3 conversion factors because we have these 3 spots that we have to jump through, or 3 hoops we have to jump through. If we're starting with grams of aluminum up top, we're going to need grams of aluminum on the bottom, and we're going to have the molar mass of our aluminum because we said we have to go to moles of aluminum. So 1 mole of aluminum, how heavy is that? It's going to be 26.98 grams. And we get this number from looking at our periodic table. So again, we have grams of aluminum to start with. We have grams of aluminum that we'll end up converting to. And then from grams, we're going to moles. Okay, so we have 1 mole of aluminum up top in our equation. And so we're going to need moles of aluminum at the bottom. And this is where we bring in our mole ratio. In my balance equation, I know that I'm going to need 2 moles of aluminum. Here they are. And we're trying to convert over to hydrogen. So how many moles of hydrogen do I need? 3 moles of hydrogen over there. And that's where I get the 3 down here from, and that's where I get the 2 down here from. And then if I'm trying to go from moles of hydrogen to liters of hydrogen, here's my moles of hydrogen up top. I'm going to need moles of hydrogen at the bottom. So how many liters does a mole of hydrogen take up? And a mole of hydrogen always takes up 22.4 liters when we're talking about standard temperature and pressure. And in terms of chemistry right now, we are always going to be talking about standard temperature and pressure. I'll let you guys know when we're not. Otherwise, we can assume that it's standard temperature and pressure. All right, and so if we multiply 2 times 1 times 3 times 22.4 and divide that number by 26.98 times 2 times 1, we'll get 2.49 liters of hydrogen gas. And again, what I should have done is I should have gone and checked that my setup is right. Here's my grams of aluminum. Here's my grams of aluminum. Here's my moles of aluminum. Here's my moles of aluminum. Here is my moles of hydrogen, and then I end with my liters of hydrogen, which is what I wanted to end with, which is my volume of hydrogen. So all of my units crossed out, so I have slowly gotten to my answer correctly. Okay, let's clear the screen. And we can also go backwards. We can do volume to mass stoichiometry. So here I have 2 CaO solid added together with 2 SO2 gas and O2 gas, and that is going to yield 2 CaSO4 solid. So we have calcium oxide along with sulfur dioxide along with oxygen is going to produce calcium sulfate. So calcium oxide is this product that we use, or reactant, I guess, that we use to remove sulfur dioxide. You make sulfur dioxide when you burn coal inside of a power plant. It's just a waste product that's made. And the sulfur dioxide, if it goes up into the air, it can cause acid rain. So we want to get rid of that sulfur dioxide so it doesn't go up to the air. So they will use, in the factories and the power plants, calcium oxide to try to combine with the sulfur dioxide. So how much calcium oxide would Natalie need to react with 1.4 times 10 to the third liters of sulfur dioxide? And again, we write out what we know, what we don't know, what we're trying to figure out, and we solve, and then we check to make sure our answer makes sense. So what we know is we have 1.4 times 10 to the third liters of sulfur dioxide. We can figure out the mole ratios from our balanced equation, and we can figure out the molar masses using our periodic table. What we're trying to figure out is the grams of calcium oxide. So let's go ahead and do that. Okay, so what's our setup look like? We're going to go from the volume of what we're given to the moles of what we're given, which is sulfur dioxide, to the moles of the unknown, which is going to be the moles of calcium oxide, to the grams or the mass of the unknown, which is calcium oxide. So you might want to pause this video so you can set this up yourself. And then I'm going to show you how I set it up. We're going from liters of sulfur dioxide to moles of sulfur dioxide to moles of calcium oxide to grams of calcium oxide. So here we go. Starting with what we know, 1.4 times 10 to the third liters of sulfur dioxide. Liters of sulfur dioxide are up top, so now they're going to need to be at the bottom of my next fraction. 1 mole of sulfur dioxide is going to be 22.4 liters of sulfur dioxide. Again, where did we get that from? This is going to be the volume that all gases take up at standard temperature and pressure. 1 mole of any gas is going to be 22.4 liters. Okay, so what's next? We have moles of sulfur dioxide up top, so we'll need moles of sulfur dioxide on the bottom. And this is where we bring in our mole ratio. So according to our balance equation, we need 2 moles of sulfur dioxide to go with our 2 moles of calcium oxide. And that's where my mole ratio comes from, down here. And if we have moles of calcium oxide here, we're going to need moles of calcium oxide on the bottom. And this is where we're going to use molar mass. 1 mole of calcium oxide, how heavy is that? Because we're going to mass in grams. That's going to be 56.08 grams of calcium oxide. And how do I calculate that out? I'm going to have to look at my periodic table. And calcium oxide contains 1 calcium and 1 oxygen. So we add those together, and that should be about 56.8. And if we do our math and we multiply, we'll do 1.4 times 10 to the third times 1 times 2 times 56.08, and then divide that by 22.4 times 2 times 1. And that should give us 3.5 times 10 to the third grams of calcium oxide. All right, so that is it for this set. What you can do next is you can check your notes. Are all the boxes and blanks complete? Check yourself. Do you feel like you understood the information? And then you can check your skills. You can go over to Canvas, go to quizzes, take the skills checks. And if you score less than 75%, that means if you get less than 3 out of 4 right, you have to watch this video again. You don't have to do the whole thing, just parts of it that you don't understand. You can ask for help from a friend or from your teacher, or you can YouTube another video of any of these topics for extra help. All right, good luck.